Fantastic. All right. So thank you, Sharon. So I'll be describing what essentially is a case study and how we're combining EXAFS modeling, and by modeling I mean ab initio molecular dynamics simulations of EXAFS spectra, and aberration corrected TM to provide, we think, are truly unprecedented details on the coordination environment of metal impurities in iron 3 oxides and oxyhydroxide. But for this talk, I'm just going to be focusing on uranium and hematite. And the next slide should be up. I don't think I have to tell anybody here how important iron oxyhydroxides are for controlling coupled redox cycles in the near surface and transport of minor but critical metals in the subsurface. There is a real need for detailed information on the local coordination environment of impurities. This would inform host phase properties, fate and transport, including biogeochemical cycling of essential micronutrients and trace nutrients. Also waste forms. Iron oxides are being considered as waste forms for actinides. And perhaps not of interest to this group, but there's a large industry, there's a large effort to tailor natural oxides for industrial uses, for example, photocatalysis, using doping iron oxides, natural oxides, in that process. However, there are lots of knowledge gaps still, despite decades of work in this field. And I would say that how impurities are incorporated in iron oxyhydroxide is actually not well constrained. In many cases, we don't even know if they're incorporated or what structural sites they're in, whether they're occluded or adsorbed, or still can be open questions. The role of defects and charge compensation schemes in accommodating impurities is not well laid out, and also not as well laid out as a function of incorporation pathways. And most of the information really is on laboratory experiments. I do have an extra slide, if there's time, after my conclusions to show some very recent information on uranium incorporated on natural hematite. So the kind of information we're after, and I won't be talking about zinc, but I like this illustration, is here we have zinc incorporated in hematite, and through this AMD-informed EXAFS approach, what we've discovered is that the zinc is embedded in a protonated iron vacancy configuration. We know exactly where those protonated iron vacancies are. We've got corner sharing, we've got edge sharing protonated iron vacancies, and the charge compensation scheme is a proton. So zinc 2+ substituting for Fe3+, you need an extra charge. And we know exactly where that proton is. It's in an interstitial site, a next nearest neighbor interstitial site. So that's the kind of detailed information that we're looking for here using this technique, or these combination of techniques. All right, so basically it's an illustration of why the AMD-informed EXAFS approach is so powerful. And it addresses the problem of lack of constraints in fitting EXAFS, particularly for unprecedented bonding environments, such as an impurity in an iron oxide. So the entire conversation here is going to be about uranium-6 that's associated with hematite after low temperature co-precipitation experiments. And my interest in the AMD approach arose because basically of a paper in 2014 by Marshall that basically contradicted both Duff and work I did in 2012 in collaboration with John Barger and his group. And basically over 12 years, three different studies, but the EXAFS was nearly identical for all those studies, 3 different interpretations, basically identical EXAFS, all right? All 3 studies used very high Debye-Waller factors for the first shell, and we ignored charge balance constraints for good reasons. We didn't have the statistics to go after that. So this motivated me, in particular, Marshall's paper. It came from, this is a group from the University of Michigan, Manchester, who said that Duff and Ilton got it all wrong. So I'm an experimentalist, and I called in the cavalry, and the cavalry is basically theorists in this case. I want to call out Eric Balaska in particular. He's a primary developer for Northwest Chem, and he's responsible for the ab initio molecular dynamics code there. He used to be an EMSL, he's moved into PCSD now. I also want to call out Martin McBride, a postdoc who's now at Intermolecular. It's a high-tech company in San Jose, and Sebastian Karasit, who's a colleague in our geochemistry group. So one of the advantages of simulating EXAFS using AMD is that the thermal disorder is baked in, so we can focus on the configuration space. So in short, you do the AMD, you pick a configuration, you can pick any configuration you want, put your range in any site you want.
You have entered as an attendee in listen-only mode.
Simply continue to enable the behavior.
I have no idea what that means.
Very often we see.
Am I okay?
You're good to go. I think somebody actually didn't mute themselves.
Oh, okay. So what you do first is you pick a configuration, any configuration, right? So, and you start your ab initio molecular dynamics simulations. We run it for about 20 to 30 picoseconds, and we're sampling it every 60 femtoseconds for a total of maybe anywhere from 200 to 400 time slices. You then stick each individual time slice into FEF, generate a EXAFS spectra, and then you take the average of the entire ensemble. Okay, and you use that in linear combination fits with other AMD generated EXAFS, or you can also mix it up with some experimental EXAFS. And the right is sort of an example. Here we put uranium into iron 3 site in goethite. And that left panel here where it says oxidation states and charge compensation schemes, we put in U4, U5, U6. In this octahedral site, it's the green ball highlighted by the big green circle. We used a proton deprotonation scheme. So uranium 4, we took out 1 proton, for uranium 5, 2, and for uranium 6, we took out 3 protons. And one of the important things to notice is that these oxidation states are very distinct, but it's not so much the atom distances, it's the amplitudes. And that should be a little bit of a warning, because if you use the Debye-Waller factor as a fitting parameter, you're going to be missing a lot of the story. So it's the amplitudes in this particular case here that distinguishes the oxidation states, not the atomic distances so much. We can also capture KT accessible states. So this small green circle, inside there's a gray ball, that's a proton. That proton turned out to be mobile, and it's bouncing back and forth between a uranium octahedra and an iron octahedra. And this is for U5 simulation only. That's the bottom right panel. And it spends a lot of time, more time on the uranium octahedra. If you were only to model the spectra, when the proton is on the uranium octahedra, you get this blue curve. If you're only to model the spectra when it's on the iron octahedra, you get the red curve. And of course, the true spectra is the weighted average of both. That's something you're going to miss if you're not doing a dynamical calculation. Okay. Of course, we benchmarked this, and one of the benchmarking exercises was to do AMD simulations of the uranium L3 EXAFS for UO2 or uraninite. And you can see we did a very good job of it, particularly at low temperature. And we get the right absolute amplitudes and the right relative amplitudes for the first and the second shell. And if we look at trajectories over a bigger volume, we can actually get structure out to above 6 angstroms. We raise the temperature, we can get the decrease in the amplitudes and also the switch in the relative amplitude between uranium, the first shell and the second shell as well. So that was very encouraging. So now we're going to go back to this uranium-6 hematite system where we had 3 different interpretations with basically the same data. What we found by applying the AMD-informed EXAFS approach is that it's basically 50% adsorbed and 56% incorporated, despite the fact that we hit this with a carbonate solution and also acidic rinse solutions. Of that 56% that was incorporated, the common motif was trans corner sharing vacancies. iron vacancies that are opposite each other. And what that allowed to happen is that we basically got a shortening of these bonds so that it started looking a little bit uranyl-like. It wasn't 180 degrees like you'd expect with a strict uranyl structure. It was bent at 170. So we're calling this a uranyl-like structure that's accommodated by these trans corner sharing vacancies. But it was more than one configuration. 30% we also needed a bulk vacancy, and 26% we needed a phase sharing vacancy. And interestingly, the phase sharing vacancy was more stable than the bulk vacancy, but the bulk vacancy was dominant. So if we go back to the 3 previous studies and compare it to the truth, you can see we were all wrong to some degree. And I'd like to give a shout out to Team Barger and Juan Pacheco Lozama, because I think we got a little bit closer to it because we did recognize the fact that there was a significant amount of absorbed uranyl in this system. And I'd like to point out that this study actually became a BER highlight, much to the chagrin of my program manager in BES, Paul Baer, beat him to the punch. I think this highlights the fact that this truly was a BER-BES collaboration in many ways. So you'll notice, well, you might have noticed it wasn't a perfect fit. I mean, it was a very constrained fit, and so there's an excuse for it not being a perfect fit, but did we miss something? That's a fair question to ask. And is there any way to check these, the AMD-informed EXAFS approach here? And so we're kind of lucky that uranium has a very high Z contrast with both iron and oxygen. So we can use STEM HADF and we can actually visualize uranium atoms. And this aberration corrected TM is another EMSL resource that we used. And to sum it up, basically it's consistent with our AMD EXAFS approach. And I'm going to go through this in a little bit of detail. So if you look at the upper left micrograph here, what you should see is basically it's an off-zone axis image. The scale bar is 2 nanometers. And the bright spots are uranium atoms. And the low density, sort of darker patches are voids or pore spaces. And you can see that some of those uranium atoms are clustered around or in these voids. We think that that's that recalcitrant uranyl that you just can't get rid of with either a carbonate or an acid rinse. You look at the bottom left panel, you see these bright spots. Those are columns of iron atoms, and every now and then, arrowed, you'll see a bright spot. That's a uranium atom that's either sitting in the structure, substituting for iron, or on top of an iron site, on top of an iron column. Backing up our AMD results, or our AMD EXAFS results, saying yes, uranium is substituting for iron. And hopefully this movie works. So, you know, the beam is injecting a lot of energy into the sample, and actually you can do time-lapse study and you can see the uranium atoms start to bounce around. And I'm gonna just let me know if that movie's working for you guys. A little feedback.
Yeah, that looks good.
Okay, great. So you see those bright spots. Again, this is basically off-zone axis. So when you go off-zone axis, you're looking through a less dense, it's less dense. So the uranium atoms stick out more, like Christmas lights or street lights. And you can see that some of those atoms are moving a lot, particularly around, it's not exactly a void space, but if you look at the edges here, you can see uranium atoms are really bouncing around. In some places, the uranium atoms are bouncing around very little. So we had a very talented postdoc, Elias Nakuzi, who's now transitioned to staff, and he wrote his own image analysis program. And what he discovered was that about 59% of the uranium atoms moved less than 4 angstroms, and 41% moved more than 4 angstroms. And for reasons that I'll explain later, we think that those relatively immobile uranium atoms are probably incorporated. And if you recall, the AMD-informed EXAFS approach gave us 56% incorporated. So we're getting a very nice correlation then between the dynamical TEM study and our AMD-informed EXAFS approach. And that's very encouraging. So I shall go to the next slide. Okay, what about a little bit more detail here? We claimed through the AMD EXAFS that the uranium was embedded in a iron vacancy cluster, all right? So here we're looking down the 4,2-bar 1 zone axis. Again, the bright spots are columns of iron atoms, and every now and then you'll see a little brighter spot, and that's a uranium atom sitting, we know it's inside the structure. And if you focus on what's going on inside the red and the blue circles, I'll turn this movie on. Again, this is the energy of the beam, and you can see that the light, it's sort of blinking on and off like a traffic light. In this case down here, you can see it's going up and down, the bright spot here, up and down, blinking on and off. And the lower right, you can see it's going up and down, but also it's going diagonally. Okay, so this uranium atom's mobile, it's bouncing around. And what we think is happening here is that it's going into these vacancies that we claimed from the AMD-informed EXAFS. To complement this, we did AMD study, which we raised the temperature in order to try and match the energy of the beam. And so on the right side, you'll see an AMD simulation of this process where we used the AMD-informed EXAFS configuration as a basis. And we just started raising the temperature until these atoms started moving around. And the yellow is the uranium, blue is a mobile iron atom, and the brown are iron atoms in the structure. Okay, and it's the same zone axis as in the experiment to the left. So I'm going to turn this on. You see things start moving around. And first thing that happens is that this blue ball, it's an iron atom, becomes mobile. And it scoots over, and I'll stop the movie right there. It scoots over into one of those trans-corner sharing vacancies, which are perpendicular to the page, right behind the uranium atom. It scoots over there, which means that we now have a vacancy and an edge site where the uranium could go into if it wanted to. It doesn't. I think we should have gone to higher temperatures and longer simulation time. It doesn't actually go over, but it can go over, and that could simulate this diagonal hop. Unfortunately, like I said, we didn't run the simulation long enough. But it could have happened. So I'm going to go this again. And now that iron atom, which is mobile, is going to go back to its original site and close off that vacancy anytime now. And I guess I should have speeded this up. And now it's gone back to it. It's closed off that vacancy site. And now the uranium atom is going to hop down into that phase sharing vacancy below, which we know is a phase sharing vacancy. We've also done simulations off zone axis tilted, and we can actually see that the uranium atom goes into that phase sharing site as the 3 oxygens sort of breathe open, the uranium just sort of skirts right through. Okay, so I think this combination tells us the AMD EXAFS approach it's very robust. We think we can be trusted now in the general case. In this particular study, we've bridged scales. We've gone from atoms and STEM hadaf to, well, basically molecular. Go ahead.
2 minutes.
Okay, to sort of more of a bulk sample, still molecular scale, but bulk molecular scale, which would be EXAFS. Okay, I'm going to sum this up. I think sort of show you we can get unprecedented details on the local coordination environment of impurities. We have pulled out some general principles just for the hematite and oxidizing system. Protonated iron vacancies help accommodate impurities. I haven't shown this data, but it's in the case of zinc, it's very robust. Those protonated iron vacancies survive to very high temperatures, annealing temperatures, 500 degrees centigrade. Very important is that configurational disorder is the rule. So it's kinetics and metastable configurations. So using energetics to try and narrow down configuration space could be problematic. In some cases, the host phase and impurity do reach a compromise in terms of symmetry considerations. The big issues are the very large configurational space to search. There are some ways to narrow it down. And AMDs are expensive, so we're using these small cell sizes, which can introduce some artifacts due to correlated motions. And in neighboring cells. It's a periodic boundary approach. There are neighboring cells, and you can get some amplification at higher R and get some amplitude where there shouldn't be any. And I could close it out there. If anybody wants to discuss this, there are some ways of narrowing the narrowing the configuration space to search. I'd be happy to discuss that offline, or if there's time during questions, I could go back to the slide. And just want to thank everybody. This is truly a BES, PNNL, BER, SSRL, EMSL collaboration. EMSL, thank them for the Northwest Chem Code and expertise. The aberration corrected TM is an EMSL facility, and of course used wet chemistry facilities in EMSL. SSRL, the early paper, 2012, we did the EXAFS work there with John Barger's group. The University of Manchester group, Sam Shaw's group, donated some EXAFS for the 2018 paper. We all became friends after a while. And of course, my own BES Geosciences program at PNNL. Thank you.